Okay, Math 30-1 students, how are we all doing on this transformations unit? Well, guess what? We're nearing the end. We are basically, now that we know how to translate, reflect, and stretch these graphs, we're going to put all of those together in this lesson and the next, combining transformations. Okay, so that's the idea with this lesson. All right, so first of all, they summarize that a little bit up here in this area here, but then they go through some investigations. For the sake of time, we're going to skip the investigations and get right to the examples. Actually, there's some summary notes first we're going to look at. Okay, on this page here, page 131. So in your workbook, you're going to switch to that page, and we're going to discuss the review notes. Okay, so what they found out through those investigations was the following about the order of transformations. Okay, so when does the order of transformations matter? It matters when a translation, moving left, right, up, down, and a stretch, okay, in the same direction are combined. Okay, so if you do move up and a vertical stretch, then the order matters. You'll get a different graph if you do it in a different order. Okay, the other one, most reflections and translations, when you combine those, also the order matters. Okay, now unless otherwise indicated, if you're just given an equation and you're asked to draw the graph, the order in which you would do these transformations are as follows: stretches, reflections, translations. And I mentioned this in a previous video. How do you remember that order? Think of the word sort. Okay, ignore the O. Stretch, reflect, translate. Sort it out. What order do you do it in? Sort it out. Okay, so let's look at example one. Describe a series of transformations required to transform graph A to graph B. Okay, so you have to think about the different transformations we have: stretches, reflections, translations. First of all, stretches. When you're looking at that, you're looking at the general shape of it, or some dimension of it. Has that dimension changed? Okay, because if it has, then it's been stretched. So let's take a look. Well, it kind of looks like these parabolas are exactly the same size. Let's compare over 1, down 1, over 1, down 1. Yep. Okay, they're the same size. So you know what that means? There were no stretches. Now, we don't really need to write that. I was going to write that down, but we're just going to write down what was done to it. Okay, so stretches, nada. Reflections. Okay, so for reflections, you look at the orientation of the shape you're examining there. So has it changed orientation to go from A to B? Yes, it has. It looks like it's facing the other way. So we would have taken graph A and reflected horizontally or reflected over the y-axis to get it facing in that direction, right? So we have a reflection over the y-axis. Okay, now last transformation, translations. Okay, we need to figure out how far this graph, the reflected graph, mind you, you always have to do the stretches and reflections on the original graph before you determine what the translations would be. So we didn't stretch it, we reflected it, and this is a pretty good anchor point right here to determine where it went to on the other graph, which is this anchor point there, the vertex. So how's it moved? It looks like it moved 1, 2 to the left. Okay, so it went left 2 and 1, 2, 3 up, or up 3. And there we go. Describe a series of transformations. Done. All right, example number 2. Describe a series of transformations required to transform graph A to graph B. Okay, so let's take a look. Graph A to graph B. So check out the shape to determine the stretch. All right, definitely a different shape horizontally, but vertically this height of 4 and the height of 4 didn't change, right? So horizontally, this width of 4 is now a width of 8. So how did we get from the number 4 to the number 8? We multiplied by 2. So would that be a horizontal or a vertical stretch? Well, it's in the horizontal direction, so it's going to be a horizontal stretch by a factor of, excuse my messy writing, by a factor of 2. Good. All right, now we need to do that to a point, or we could use the middle of our square on A, go to the middle of the rectangle on B in order to determine the transformation. How come we can use the middle? Because if we horizontally stretch about the y-axis, that point there does not move. Okay, so how far did it move? It went 4 left, 7 down. So left, 4, down, 7. All right, why don't you guys try B and C, and then we'll check and see if we have the same answer, okay? Pause your video now, please. All right, so part B of example 2, we have a vertical stretch by a factor of 2 going from graph A to graph C because it's twice as big vertically. And then if you take that center point, which wouldn't have moved after a vertical stretch, and then figure out where it went to on the center point of box C, that would be left 6 up 4. Hopefully everyone did okay on that one. Next one's a little bit trickier, graph B to graph C. We don't start off centered about the origin, so there's a little bit of a twist on this one. Now you could do it with, like I showed here, vertical, horizontal stretches and then translations. You could also do a reflection about the line y equals x. I don't know if anyone out there thought about that. Which is a great way to do it, and then translate it. You could also reflect it over the x-axis, then stretch it. All sorts of possible combinations of getting box B to box C. But let's say we do this version of it. Horizontal stretch by a factor of 1/2. Why did I do that? The box was 8. I needed it to be 4 across horizontally. So we did that. Vertical stretch by a factor of 2. The height of the box was 4. I needed the height of the box to be 8. So stretch it vertically by a factor of 2. That's all good. Now, how many of you put 1, 2, left 2, and up 11? Yeah, I knew some people did that. Here's the scoop. You can't do that because this center point that we've kind of been using all along would have moved after we horizontally and vertically stretched it. So we actually have to figure out where that point would be after we do the stretches and then figure out the translation. So horizontally stretched by a factor of 1/2, we're a distance of 4 away from the y-axis, or x-coordinate's -4, then x-coordinate would be -2. Okay, y-coordinate, we vertically stretched by a factor of 2. It was a y-coordinate of -7, stretched by a factor of 2 times 2, -14 now. So now if we take this point that is at -2, -14, and I want it to be at -6, 4, how do I get it there? Well, to go from -2 to -6 for x, we would have moved left 4. To go from -14 for y to +4 for y, we would have had to add 18, so up 18. And there we go. All right, let's look at the next page. Okay, example 3. Describe which transformations are applied to the graph of a function when the following changes are made to the equation. Does the order in which the transformations are performed affect the final graph? Okay, so which transformations are applied when the following change, so we have to describe the transformation. So we replace x with 3x. Okay, so x, we're talking horizontal, right? So horizontal, and we've got a number multiplied by x in the replacement. So that's going to be a stretch, okay? And when it's with the x, it's upside down, right? So horizontal stretch by a factor of 1/3 about the y-axis. Okay, and then we replace y with y plus 4. So we're talking y, that's going to be something vertical. We're replacing it with y plus 4. So the plus and minuses were the translations. So this is going to be, if you want, you can put vertical translation. You don't have to. Obviously, if you say up or down, it's vertical. Y with y plus 4. Remember, upside down and backwards. So this one's backwards. You would think up 4. It's actually down 4. Good. Now, does the order in which the transformations are performed affect the final graph? We've got a stretch horizontally, and we've got a translation vertically. Okay, if those were in the same direction, then it would matter. They're not, so no, order does not matter. Okay, let's look at B. Why don't you guys fill in? Oh, I'm giving you guys the difficult one, aren't I? Anyways, give it a good try. Replace x with 2/3 x, y with negative 3y. Notice that negative and the 3 are two different transformations. And then x with x plus 2. Okay, let's write down the transformations for that, and we'll check back and see if we have the same, and take a guess at whether the order will matter. Okay, so pause your video, please. Okay, so we should have horizontal stretch by a factor of 3/2, vertical stretch by a factor of 1/3. The negative would be a reflection in the x-axis, and replacing x with x plus 2 moves it left 2. Okay, so hopefully we all had the same thing. Now, does the order matter? If stretches and translations happen in the same direction, then order does matter. So because we stretch horizontally and move left, so horizontally, yes, order matters. So yes, order matters. Okay, great. Let's look at example 4. The graph of a parabola y equals x squared plus 1 is shown. The following transformations are applied to y equals x squared plus 1 in the order shown. Okay, so sorted out, SRT, doesn't necessarily apply it. We have to do it in the order in which they say. Okay, so first of all, they say horizontal translation 2 units left, reflection in the x, yada yada, and they want for each transformation, graph the image on the grid. Hopefully you have your colored pens out, and then write the replacement for x or y and the current equation. So I'm going to run through the first one with you, and then you guys can do the rest. So horizontal translation, 2 units left. So first of all, let's make some anchor points we're going to use. So where I'm putting dots, you're going to want to put dots as well. Okay, those points are what we're going to be transforming. Okay, so left 2, we're going to move each of those points left 2. Okay, and then we're going to draw the new graph. And there we go. Draw the new graph. Hopefully better than what I'm doing. Okay, something like that. All right, and the replacement, if we move left 2, x gets replaced with x plus 2. And in the equation then, which was y equals, actually I'll write the original up here, y equals x squared plus 1, would now be scoop out the x squared, put in the new x of x plus 2, and there we go. That would be our new equation. Don't expand that, it's just going to complicate things. All right, so you guys go ahead and continue on with reflection in the x-axis, vertical stretch about the x-axis by a factor of 0.5, or think of that as 1/2, and a vertical translation 3 units down. Okay, and fill in the table as you go as well. Use different colors, it will make things easier, and we'll check back and see if we have the same thing. Okay, what a colorful graph. Does yours look like that too? Okay, so our final equation or graph should have ended up this purple graph here. The vertex would have been at -2, -3.5. Okay, so follow through and see if your points match up with mine. If not, pause the video and try and correct what the situation is. Okay, so now we are going to look at the next part. Okay, write the equation which represents the final position of the graph and verify using the graphing calculator. If we're going to do that, we need to isolate y in that equation. So we're going to go about doing that here. I'm just going to work down from there. So first I'm going to divide by -2. So we would have y plus 3 equals, now dividing this term by -2, we have to put it on the outside as -1/2. Okay, divide 1 by -2, we'd get -1/2. And there we go. Then we're going to add 3 to the other side, and we would have y equals still -1/2, not -1/3, x plus 2 squared, and then subtract 3, so minus now 3.5. Okay, so what we're going to do, oh, actually, if you look at that, the vertex, you can tell, is going to be -2, -3.5, just from our standard form of the equation, remember? 20-1. All right, check it on the graphing calculator. Make sure it looks the same as our final graph. And woohoo, you are done. Good job, everyone.